Hey guys, welcome back to Astronomy Day, and today we'll be talking about a hell of a strong subject, neural networks. It's gonna be tough, but we're gonna do it. So, good luck. Hope you stay alive. Before we begin, you guys must be wondering what the heck is a neural network? It is a type of artificial intelligence which, when given some input, gives some outputs. But the outputs might not be correct if the network is not trained, and the name it says neural network. So, but when we train the network for a specific inputs, with specific outputs, so it basically creates the function between the inputs and outputs. In my case, I'm using back propagation network, which is into say latest term, learn by your mistake neural network. That you know it, let's get to its structure. It has some circles in it as shown here. These circles are called nodes. Sorry, my finger. So these circles are called nodes, and we have specified some certain names to certain nodes. The first is the inputs, the last row is the outputs, and anything that comes in between is considered under hidden layers. Well, hidden layers is divided into hidden nodes. As by the name you can guess, the nodes present in hidden layers. So that's that. And now you can also lines, the blue line specifically. Those connects two nodes together. These lines are called weights, as shown. So it's not that complex of a structure, but we'll get to that later. So now, as you can written lots of things on the board, don't worry, it gets first. We'll be taking a smaller example. You can see we have one input, hidden layer, and one output, and the hidden layer has one hidden. I will specify the input within I. The hidden node and output you can see are divided into the dark and the white side. The dark side is capital H and the light side is lowercase h. The output, similarly, the white side is O and the dark side is O dash, the little hyphen on top. So you be confused like what the heck is this? Well, as you can see below that, H is equal to activated small h. O dash is equal to activated O. Well, what is activated meaning? So it is when input is sent through a function. It is called an activation function. The activation function then squashes whatever the input it has between some upper and lower. For example, a great example which is used very often is the sigma function. And over on that side, you can see the graph. As you can see, any number you put in, it either goes to 0 or to 1 or in between. So that's the sigmoid function, and in the corner there, it's the function 1 over 1 plus e to the power of negative x. So simple as that. So before we actually jumping on to the learning bit, the exciting mathematical bit, we have to back and appreciate how the output is calculated. The previous diagram shown was slight in error because there were notion of bias. So you're saying what the heck is a bias? Bias is usually it's not a constant, but in our case we'll constant. It's just a number, like it's 1, that's 2. It's 0 0.2, 0 0.6, it's just a number which is slightly modified along the way. It helps the neural net not be stuck. Yeah, that's basically it. It helps so that the neural net does not get stuck while learning. So we continue. That's beyond the scope and how it does, so I won't go into that. But here's how it's calculated. The input multiplied by the weight one and the bias is added to give h, the small h. Then the capital H is given by the sigmoid of the small h. Symbol is commonly written as S of H because who writes sigmoid? So again, cycle is repeated. O is calculated by H into the weight plus bias, but it's bias obviously. And the real output O dash is calculated by the sigmoid of O. So that's how this is calculated, just 4 lines in our case. For right now and this video, we'll only focus on one hidden layer and multiple inputs and output nodes. Also multiple hidden nodes, that's gonna get a bit complex. We'll see about that later. We're also going to partial differentiation and how the chain rule is applied in this real action of chain rule, which is very exciting and very beautiful. So let's continue on the learning bit. For any input 1, it has to give 0. Wait, it isn't trained, so it gives like 5 as an output. Totally wrong. So how do we tell that? It's a machine. We can say it, you're bad. So what we have is we have another node. This node is called the desired output, or why? It is not a proper node because it isn't connected to any other node, but it has a very important part to play. It helps us figure out the error, the total error, that how close are we to the actual answer. This is figured out by this formula. The error is given by the desired output minus the real output to the power 2 and then divided by 2. The power 2 is added because when we differentiate the error later, the 2 that comes down gets cancelled. So by adding the constant here doesn't change a thing. And now this is our error. We know how wrong it was. So now all we have to do is change the weights. Change the input, but you can't change the weights. So we have calculated the error. We want to know how much change is required in weight 2. So how do we do that? We take the partial derivative of the total error with respect to weight 2. So which is written as, it is given by this formula. This monster. It's not a monster until after you learn it. So the total error and the weight, how are they related? Well, they are related by this. And you're wondering, what the heck do you do this? How does this explain? So the error, we find how it affects the weight, or how the weight affects the error. So what we do is we take the partial derivative of the error with respect to weight 2. So how do you do that? So you can see the error is not directly connected to the weight, but it is connected indirectly. The error is also connected to the output, which is connected to the unactivated output, which is then connected to the weight. So using the chain rule in partial derivation, we can say that the change in error with respect to weight 2 is equal to the change in error with respect to the output multiplied by the change in the output by the unactivated output multiplied by the change in the unactivated output because of weight 2. So if you solve this, you'll get how much the total is changed with respect to weight 2. So that's how it is derived. A quick calculation shows it is equal to this bottom row. See, simple as that. So there you have it. That's how you do it. But that's weight. It's only weight 1. What about weight? Sorry, that was only about weight 2. What about weight 1? We do the similar way. The rate of change of total error with respect to weight 1, or the partial derivative of the error total with respect to weight 1. If you follow back all the way, that is error out, the unactivated output, then this, the hidden node, the unactivated hidden node, then the weight. We don't take the weight in between, so we just take the nodes. So can you guess what this will be equal with weight 1? There you go. That's the correct answer. You've got it. Well done. You know what partial differentiation is. Chain rule of it. So it is equal to this monstrous equation. It's comparatively monstrous. And it comes out to this. Isn't it just wonderful? So now you know what this is. You know how much you need to change weight 2 and weight 1. But how do you do it? You just can't just replace it. That would totally screw up the network. But there is a way, I'll tell you. So this is how you change the weights. Weight 2 becomes weight 2 new, which is equal to the previous weight minus alpha into the change. Same, weight 1 becomes weight 1 new, equal to weight 1, the previous weight, minus alpha into the change required. But wait, what is alpha? Boom, alpha is equal to learning rate. So this is basically how it learns. You do this one time, error might change by slight. Suppose it was previously 0.6. It might change to 0.58. Not big of a difference. But if you do it enough times, you can change everything. Soon it will start to learn about what the function is. That is I with O. So this is how it works. And if you're hearing some echo, it's because of an empty room. Anyway, as homework you might say, I challenge you to find how the bias updated, the bias 2 and bias 1. I'll leave the answers in 3, 2, 1. So these are the answers. Boom, very easy. Same pattern you just follow. And that will be all. So before I end the video, I would just like to say a special thanks to my friend Franzi. She's from Germany and she gave me the idea to make this video. Thanks a lot and I will see you next.